Hi, this is Team 10's video report for Experiment 5. Team 10 consists of Gabe, Sean, Noah, and Josh. For this lab, the software Xfoil was used to compute a number of variables to select the best design in a selection of wings for a remote-controlled airplane. These determining factors are the lift and drag coefficients based on the shape and angle of attack on the wings. In order to compute these variables, the Reynolds number and Mach numbers must be known. These numbers are 315,000 and 0.12 respectively. This lab deals with two selections of wings, the first being the S1223 and the second being the S1223 RTL. The geometry was given as a reference from airfoiltool.com, and the plots of the wings geometry are on a scale from 0 to 1, derived from the dimensions of the wing being divided by the chord line. With the scale, the leading edge is at 0 and the trailing edge is at 1 for both wings. The main geometry is given by the blue line, with the mean camber line in the orange and the chord line in gray. The design of the wings also leads the suction surface to be the top side of each wing with the pressure surface on the bottom.
My name is Noah Toth, and this is part 2, where we compare the geometry plots of the two airfoils. Now we can see that the two airfoils are very similar in size and shape, except that the thickness of the RTL airfoil is slightly thicker in some points, noticeably here at this front hump, also in the bottom at around 0.4 x over c, and that it has a slightly longer tail. If we look back at lecture notes, we see that the cambered airfoil is going to have a lower angle of attack necessary to generate lift, and this is from a symmetric airfoil. Now if we imagine the symmetric is just raising that camber, so we can insinuate that with the RTL airfoil having a higher hump in the front, which is kind of a symbol of having a higher camber, that this will likely lead to a lower angle of attack necessary to generate lift in the RTL airfoil, which is an extremely attractive trait in designing a model airplane.
Here we're aiming to observe the relationship between the lift coefficient as the attack angle changes. We can observe for both airfoils a general exponential inverse relationship between the lift coefficient and the attack angle. A point of interest on these plots is the first decline after the peak. This is indicative of an attack angle where the airfoil begins to stall. In the case of S1223, this is right around 15.5 degrees, and for S1223 RTL, this happens slightly higher at an attack angle around 16.5 degrees. The maximum lift coefficient in both cases is right around 2.3. This graph shown depicts how the lift coefficient of the airfoil changes as a result of changing drag coefficient. The ratio of these two values is often referred to as the lift-drag polar. We can observe that in both cases, the lift coefficient experiences a rapid linear increase as the drag coefficient increases until it reaches a maximum value. After this, the lift coefficient begins to slowly decline as drag increases. On S1223, the lift coefficient reaches its maximum value when the drag coefficient is right around 0.05, while on S1223 RTL, we observe that the max value is slightly higher, around 0.06. The lift-drag polar helps us determine the aerodynamic efficiency of our airfoil by allowing us to find an optimal drag coefficient to maximize our lift.
Here we can see the plot of pressure coefficient versus the normalized length xc created on Xfoil. In this graph, the angle of attack used is 0 degree. According to the graph, we can infer that in the graph of S1223 RTL, it reaches an area high pressure for a smaller extent of xc, which is normalized length, than S1223. Also, at the bottom of Xfoil, we can see the boundary line thickness of the airfoil profile. Moving on, next we see the graph of pressure coefficient versus angle of attack at which the airfoil stalls. Here we see the greatest drop after peak lift coefficient, and this is called as stalling. It continues to stall as the angle of attack increases. Here we also see the boundary line expanding as we calculated the angle of attack to be approximately 16.5 and 18 degree for S1223 and S1223 RTL respectively. Here we concluded that S1223 graph has slightly more streamlined stall, which allows easier recovery even though the difference is minimal.
My name is Noah Toth, and here we are deciding on which airfoil will be the best for our model airplane. And we're going to make a few assumptions. We're going to assume that because this is a model airplane, weight is going to be our greatest concern in design. Our model airplane is small enough that any amount of material or cost is actually going to be pretty small, especially when we compare such small differences in size. So with these assumptions, we're still going to go ahead and say that the RTL airfoil appears to be the better choice. Now it's technically larger, but the profiles are so similar in size that they're going to be very similar in weight. The RTL airfoil has a lower necessary angle of attack to achieve lift, which we're inferring from step 2. We can also see here that it's going to have a greater angle of attack necessary to stall, noted on the right, where its angle of attack is closer to 20 degrees, while the S1223 airfoil is closer to 15. And it also achieves a higher pressure coefficient, noted by RTL on the right with the yellow line. And this is going to mean that it's going to have more pressure pushing it upwards, which is a good thing. So while the S1223 is technically smaller and has a slightly more streamlined stall, noted in the step prior, the rest of the differences between the airfoils make the RTL airfoil the ideal choice for a model airplane. Here are our final thoughts on Experiment 5. Running this simulation has allowed us to develop a better understanding of how simulations can be incredibly useful to engineers. The ability to gather data without having to physically set up an experiment saves a lot of time and also increases the repeatability of an experiment. One could also easily manipulate and test multiple variations on whatever is being tested. In our case, it's airfoils. Thank you for watching our Experiment 5 video.